Today, we're going to explore a practical topic, verbal inequalities in one variable. In this lesson, we'll see how to translate phrases like at least, no more than, or greater than into mathematical inequalities. Understanding these phrases helps us solve real-world problems where we're asked to find ranges of values, instead of just a single number. By the end of this lesson, you'll be able to take word problems like this one and write them as mathematical inequalities that we can solve and interpret. In this example, we convert this verbal inequality to x greater than 16, where x represents age. To understand what verbal inequalities are all about, we'll focus on three main steps. First, we'll identify common phrases that signal an inequality. For example, at least translates to greater than or equal to, while no more than translates to less than or equal to. Once we know what inequality symbol to use, we set up the inequality by translating the phrase into a mathematical expression. For instance, if a problem says, the number of students must be at least 20, we write x greater or equal to 20, where x represents the number of students. After setting up and solving the inequality, we interpret the solution to answer the original question. This helps us understand the range of possible values that satisfy the condition given in words. We should also note that when the sign changes from greater than or equal to just greater than, we would indicate that with a circle instead of a dot, which means that the number specified is not included in the range of values. Let's see how this works with an example where we need to translate the following statement into a mathematical inequality: a person must be at least 18 years old to vote. Let's start by identifying the key phrase here. The phrase, at least 18, tells us the person's age must be 18 or older. In mathematical terms, at least means greater than or equal to. Now, we can set up the inequality. Since the person must be at least 18, we write x greater or equal to 18 where x represents age, which tells us that any age of 18 or older will meet the requirement to vote. We've successfully translated the verbal statement into a mathematical inequality. In this problem, we need to translate the following statement into a mathematical inequality: a student needs to score at least 70 but no more than 90 to pass. We can see that we have two key phrases to look at least 70 and no more than 90. Each phrase represents a different inequality that we'll combine to create a range of acceptable scores. At least 70 means the score must be 70 or higher, so the inequality we'll use is greater or equal to. No more than 90 means the score should be 90 or lower, so we'll use the less than or equal to inequality. This compound inequality shows that x can be any number from 70 to 90, including both 70 and 90, where x represents the student's score, and that tells us that any score between 70 and 90, including the endpoints, will meet the passing requirement. We've successfully translated the verbal statement into a mathematical inequality range. For the final example, a concert venue has a seating limit of 200 people. To host the event profitably, at least 120 tickets need to be sold. Which of the following inequalities represents the range of tickets that can be sold for the event? First, let's identify the key phrases in this problem. We see two key phrases here: the seating limit of 200 and at least 120 tickets. Let's look at each one. Limit of 200 tells us that the number of tickets sold cannot exceed 200. So, we'll use less or equal to 200. At least 120 tickets means we need a minimum of 120 tickets sold to meet the profit goal. This phrase translates to greater or equal to 120. Now that we have the two inequalities, we can combine them to express the range of possible tickets sold. Let x represent the number of tickets sold. The sales must be at least 120 but no more than 200. The correct answer is A, as it satisfies both the minimum ticket requirement and the seating limit. Great job working through verbal inequalities today. Let's recap the main ideas we covered to make sure they stick. First, identifying key phrases. We learned how to spot important phrases like at least, no more than, greater than, and less than, and translate them into mathematical symbols. For example, at least becomes greater or equal to and no more than becomes less or equal to. Second, setting up inequalities. Once we understand the phrase, we can set up an inequality. Always start by identifying the variable, then choose the inequality symbol that matches the phrase. For example, must be at least 20 turns into x greater or equal to 20. Third, compose D inequalities for ranges. When there are two conditions, like in our concert and student examples, we combine them to form a compound inequality. For example, at least 170 but no more than 200 becomes 170 less than or equal to x, which is less than or equal to 200. This helps us define a range that we can show using a graph. Finally, interpreting solutions. Interpreting your inequality solution helps us understand what values work in the real world, whether it's ticket sales, ages, or scores. This gives us a practical answer to our problem. With these steps, you can confidently tackle verbal inequalities and translate word problems into math. Practice makes perfect, so keep practicing with different scenarios.